should be at, where we should run it at. So we have our toggle switch, or your breakers right here that control your main power compressor. We can send power to the compressor when it gets a call to be on. With our thermostat, it's going to come on. We also have our cooling tower. If we don't turn on our cooling tower, how are we going to cool down our condenser? Because with this type of unit, you're going to have your hot gas discharging through here. This is just a flexible connection, so this thing vibrates a lot. And so it's so you don't break your joints and develop a leak. Right here is an oil separator. So the design on this is your hot gas comes in, this thing's loaded with oil, it's gonna be spilling, shooting some out. And if that oil builds up in here, you have this right here that's connected to your suction line. If you follow it through, it taps into the suction side of the compressor, and has a straw that goes all the way down, and that's gonna suck the oil back into the compressor before it shoots the oil. I mean, you're gonna get some oil through the system, but this will, the majority of it is gonna make it back to your compressor so you don't overheat. Then you have your pressure tap right here. That's where our gauge is tapped in so you can see the pressure. Our hot gas leaves through here and it tees off. It could go to our hot gas solenoid valves, which are gonna control when we need to defrost. I'll get back to that when we come through. Let's just follow it as the hot gas comes through. Right here is just two different styles of condensers. You could either have a tube and a tube, which is one big design. You'll have your refrigerant coming in through here, or you could have a shell and a tube where your refrigerant will come in through the shell right here. And the way this is designed is you have this tube that's going to go into the cavity or the space inside this tube, right? It's going to go all the way around the tube, and it's going to work its way all the way through the bottom of these tubes and come out this refrigerant output. The refrigerant, by the time it leaves, we still want it to be subcooled, so it needs to reject enough heat until it drops below its saturation point and condenses. So to create that, we have our water valve. This is a water regulating valve that you could control the amount of GPM, gallons per minute, that flow through our heat exchanger. The way that works is if we just put it right into the shell, we're gonna mix refrigerant and water, right? That would be bad. So what we have is this water comes in through the bottom and it stays in a tube the whole time. It's running through the middle of these bigger black tubes. You have a copper tube running through there. And then that tube U-turns and comes all the way until the water leaves out of here. So the water and the refrigerant never make direct contact, but they will be having heat exchange because that cold water is going to be flowing through the tube. With this design, similar process, your hot gas fills the shell of the container, and your cold water will come into the bottom. And you could have multiple different styles of this, where it'll have a 2-pass, comes in and comes out. You could have a 4-pass where it comes in, comes out, comes in, comes out. 4 times, you have 4 pipes in there. This looks like a 2-pass. So the refrigerant isn't, or the water rather, is going to travel through its tube, will do a U-turn and then leave and collecting heat. And then it leaves through this red hose where it's going to go to the top of the cooling tower to have evaporative cooling occur and have its heat rejected from the water. So our refrigerant is going to be cooled down just like a condensing fan would, right? But we're using water-based, water source. So our refrigerant, these are for each of our different receivers, or our condensers. And your refrigerant will be then subcooled, travel through our valves here, go through a filter dryer where we have a sight glass to indicate if we're contaminated or if we have moisture. It comes back up, and if you follow it back over here, we have another solenoid that's going to control when we send refrigerant to our defrost valve, which is it's just a TXV that's going to allow us to not have an excessive pressure drop. Because this thing's going to freeze. It might develop ice. We're going to get into cold temperatures, low pressures. And so if we run this thing dry on refrigerant and we're starving it, and there's not enough refrigerant making it back because it's collecting the coldest in, you're going to have a compressor working hard, getting really hot. So this valve will spill refrigerant into it to balance it out and keep that pressure stable before you have a large pressure drop. So your solenoid valves are then going to come through into your liquid receiver. So our subcooled refrigerant is going to fill up this tube here, or this drum. And in this drum we have this line, which is a straw that comes all the way back down, similar to the oil receiver. So that therefore it only gathers liquid refrigerant, sucking it off the bottom, and it delivers that to your typical, your metering device. In this application, we got TXVs, so you're gonna have it tees off, right? It comes up and tees off. It's actually this one. No, wrong one. This one.
It's that one.
Yeah, it's here.
Yeah, it goes down to that solenoid right there.
Our liquid valve. Oh no, I'm sorry. This will be an accumulator.
Okay.
Okay, so this will actually accumulate. No, this is our receiver. It's tied in right here. Oh, we have the option to use it or not in this trainer. You could either close it off or just directly run it. So as your refrigerant comes through, it's going to go through the liquid valves. That'll control when we want to send. These solenoid valves are going to control when we want to send refrigerant to the evaporators. If one is satisfied, it might open the solenoid valve, therefore closing the refrigerant passage.
Yeah.
Right? It closes the magnetism on the solenoid. The solenoid drops, it closes the valve, and now the refrigerant cannot travel to the evaporator that has satisfied load. Then you just have your typical evaporator operation. Air is going to be transferred over the coil. As that refrigerant has its pressure drop, it's going to absorb the heat out of the refrigerant, and the refrigerant will travel out through the suction line. You have your sensing bulb detecting your pressure to accommodate any pressure drop there and to feed the refrigerant properly. This line then leaves, and that actually comes into our hot gas accumulator, where if we need to defrost, there's two different methods of defrost it uses here. We have an electric defrost, which is basically a filament wire that runs along the bottom of the drain pan, which will be energized probably with like 120. It's going to get hot, it's going to make that water evaporate. We have another style, which is with our hot gas. It'll directly drop our hot gas into this bottom rack. If you look at the bottom of this unit, you can see the rack and the array of the arrangement of how it is. And that's going to help warm up that pan and also just evaporate the water. Then the system's pretty normal. You have an evaporator pressure regulator, so you can control when you want, or the pressure inside each evaporator. It basically works as a kind of like a check valve, and it only allows or an automatic expansion valve, where it only allows a certain amount of pressure out of it. If you set it to 35 psi, anything more than psi is just going to, or anything more than 35 is going to push it open and allow it out. So when pressure drops, let's say pressure in here is 12, it's going to keep that refrigerant in there at 12. Pressure is going to spill in, it's going to build up a little bit. It's going to get up to 15, it gets up to 20, it gets up to 30, and as soon as it hits 35 and then it hits 36, it might allow some of that psi out. It's going to. As soon as it'll be, the pressure inside the evaporator will be stronger than the spring pressure that was set.
40 though?
For a residential unit. For this, we're probably getting down to right around 5 to 10 degrees. This thing's running at.
So what about those high-end
Okay, so good, thank you. So here we have a high pressure cutout. This is just tapped in over to our high side before our metering device after our compressor. And if we ever hit excessive pressure, it gets too high on pressure, this cutout is going to kill our operation. It's going to break your line voltage, and it has an offset temperature. So let's say right now it's set at 200, just about 200. If this thing gets up to 200 psi, it's going to turn it off, and it's not going to let it turn back on until the pressure decreases 40 psi. So when we get up to 200, boom, triggered. It's not going to come back on until we're down to 160. The high side pressure resets down to 160. The unit will then close the contact and allow the energy to flow again. This one is the same thing, but for low pressure. If we exceed dropping below 10 psi, this thing will kill operation. And then you have an offset of another 10 psi, so it has to rise above 20, and then it'll come back on. And these are adjustable. You have 2 dials on top that could adjust when the cutout is, when it turns off, and then you could adjust the differential so it controls when it allows it to come back on after pressure balances back out. Then you have a low pressure gauge tapped in so we could read our low pressure, and you have a crankcase heater that's going to keep this thing warm to keep refrigerant migration, make sure it's superheated vapor coming back and we're not taking any liquid. You also have your liquid accumulator here. So if any liquid refrigerant is making its way out of the evaporator, it will be gathered in here, where you have another pipe that's not like a straw. It's more just going to be sucking right off the top, pulling the vapors off the liquid so that it could travel back, another flexible coupling, and then back to the compressor to restart the cycle. You have these valves to spill in refrigerant whenever we get into another pressure drop. Pressure gets too low. This one is adjustable as well, where it's going to allow our refrigerant to be spilled directly into our suction line. Here's the external equalizer. So we go ahead and flip it on now. Now that we know everything's going, we don't know what our valve positions are, but we can watch our pressures and see what it does. If it goes off on high pressure, here's an example. Let's turn it on. Compressor's on. Let's watch our high side pressure. What's not on?
Our cooling tower.
Our cooling tower. So our water, our pump is at our cooling tower. So we're not even circulating water through the pipes, let alone cooling down the water. So you just have standing water in the pipes that are about to start receiving heat. You can watch your head pressure. It's starting to build. You can feel the hot gas coming into the receiver and leaving as a hot gas still. The receiver is getting hot. Get the camera on the high pressure, see where we're actually at. Because if it gets above, what was the set point?
About 400 or
No, I've had a lot of calls for that kind of vibration sound.
no 200.
Take your hand off there again. Oh.
All right. It's vibrating. I just
A lot of technicians hear that noise and think, oh man, the pressure's bad. It's just a loose screw on the panel. Okay. Where's our pressure?
200.
Just shy of 200, huh? Looks like going above it. That might be a little higher than that. Oh yeah, we're a little bit above. We're about 225. Boom. Unit turned off.
Because of the pressure switch.
Yeah. And you could watch our pressure as it starts to,
down.
cool down from ambient, cooling it off. As soon as it goes below its 50 psi differential, it's going to cut back on.
Oh yeah. Okay.
It's a cut in, cut out.
And it'll just keep going back and forth like that until
It's
the tower's turned on.
yeah. So
Yeah,
if we
until
want to
it's-
cool
until
it
it's
down,
cooled down. Yeah.
why don't we turn the water on? Start circulating water. I can turn on the cooling tower.
Do we have a time delay for because the pressure switch was tripped?
We may with all these controllers on here.
Oh, there we go.
or we don't have to use it for something. My first guess. No fuses. We're on. Are you on?
Start the compressor.
Now
It's actually running through.
our pressures will stay stable. Now our fan, our evaporator fan, also has a cut-in. So it's going to allow the pressure to drop, and pre-chill, pre-freeze the evaporator, and then turn the unit on.
Our pressure's not going up.
That's staying stable now. Now watch your evaporator pressure.
Now this is getting
up
cold.
here.
This is cold right here.
You have a pressure tab here. That evaporator pressure is going to drop, and as the pressure gets lower and lower, you're going to have your temperature sensor that's mounted onto the pipe. It's going to activate the fan. Your fan is sitting there in series, ready to come on, but your temperature switch has it open right now. And as it drops in temperature, it's going to close the switch and enable power to the fans. Pass. Just got 2 more. All right, tomorrow. Or no, Monday. Monday we'll get universal, yeah? So make sure you study, what is that, type
Joe,
1 and 2?
Joe, this is freezing over here.
Yeah.
It's starting to frost up.
And if you feel right here, it's probably real cold. And then if you feel right here, well, it isn't. These aren't letting a whole lot of pressure through. I think you'll spill out all the guts if you take that one off.
Right, this is all vapor coming in, right? Vapor coming in,
It should be.
and then you said it's not going down in
The
there.
only way to check if it's vapor or liquid, how do we do that?
I don't know.
Subcool superheat.
Okay.
That's what it does.
That's what I'm lacking is
So-
that knowledge right there. I
So
mean, I don't know.
subcool and superheat. So if we were to check this, right now this refrigerant is, what is it, 134A?
Yeah.
134A at 10 PSI.
25 about right? Maybe 30.
That'll be on our pressure.
It's about 5 or 7 degrees,
That would
right?
be on our pressure. That would be on our temperature pressure chart, correct?
Yeah, your PT chart would tell you.
Okay,
but
we got the
I
gauge.
can see it here. The gauge has
Yeah.
PT, a little one. So if we're at 10 PSI, refrigerant is going to be at its boil point at 7 degrees. And if we take our actual temperature and see that it's 10 degrees, what does that mean?
17 degrees, right?
Which means it's not boiling, right?
If it's at 7 degrees when it boils,
Right.
and you take your actual temperature and it's at 10.
That means it's not boiling.
Yeah, with 3 degrees subcool.
Nope.
Superheat, right?
3 degrees superheat.
Superheat?
Because if you go above, you're vaporizing.
Yeah.
If you go below, you're subcooling.
Oh,
yeah.
So at 7 degrees, it boils, and it's at 10 degrees.
So 3 degrees.
It boiled, and it went 3 degrees higher than boil.
Yeah.
Because something will not completely boil until it's fully saturated.
Yeah.
Okay.
Right? So that tells you when it's fully saturated. It might have started.
In this, when you say fully saturated, do you mean it's
It's a-
saturated with the temperature to turn into a vapor?
Think about a water. Like if you had water on a stove and it's boiling at 212 degrees,
Right,
it'll
right.
sit there and boil for a while, right?
Right.
You can even turn up the flame, and it's not gonna. You're gonna have water in there, and you're not gonna be able to turn that water into 215 degree water or 213
because it's
degree water
vaporizing.
because it has to fully vaporize first.
Okay, yeah.
It has to give off all the latent heat. So, and that is in its state change. So as this refrigerant has the same property, it's going to try to boil at 7, and it cannot be 8 degrees unless it's fully boiled, and then we've added more heat to it.
And by that time, it's turning into a vapor.
By that point, it is a vapor.
Okay.
But if we took our temperature here, we know its state change is at 7 degrees, and we see that it's at 5 degrees.
So it hasn't changed yet.
We're liquid.
Liquid.
Yeah.
Yeah.
Because it changes at 7 and it's below 7. That means it's below and
Okay.
it's liquid. If it
Okay.
goes above, it's vapor.
Okay.
See ya, have a good weekend.
See you, Joe.
If you feel these, now you have hot gas spilling in, and that's kind of helping maintain your pressure drop. Otherwise, we would be excessively low. would be really, really low pressure. But we have our hot gas spilling in here to kind of alleviate that.
To help it.
And so with the simulator, what we could do is, you know, close valves and make situations occur. Watch it trigger at, you know, our controls.
These service valves, the high side.
This one?
Yeah.
This is low side.
Low side, and
Low side.
this
Is
high
there
side.
another one? Oh
High
yeah, I
side.
didn't even realize it. I never even noticed those.
So
Yeah.
can you hook gauges up there and put your temperature clamps on there and figure that out with the
You
set
don't
cooling?
need
or-
to. You don't
no?
need to
No?
with these on. So you
Okay,
you
okay.
have gauges permanently installed.
Okay.
So all you would need to do is take the clamp to it. Yeah.
Just to tell. Okay. And then you can tell your subcooling and your superheat.
Yep.
Right. With
Yeah,
the
that's the
temperature.
only way you have to verify it.
Okay.
There's nothing in the system. I mean, I don't think they're far off, and maybe the more advanced systems actually do have, you know, temperature sensors that do those calculations, and they tell you
Right.
those numbers,
Right.
just like digital gauges do. But for now, we have to manually do it.
Okay.